Welcome back to the next section in this unit, Unit 2, polynomials. We're going to be in Section 5.8. Our goal for today's lesson is to be able to use a graphing calculator to approximate the zeros of a polynomial function. We're also going to be looking at some ACT type questions to help prepare you not only for this unit and test, but ACT in general, the way they kind of phrase questions. So that's going to be a sub-target, although it's not listed here. Okay, here's some notes to look at or to copy down. X-intercepts, aka zeros, solutions, and roots. Turning points of a graph. Before we get to that, what are turning points? Turning points are local maximums and local minimums. Okay, and that's going to also tie in with our zeros as well. We're going to use the graphing calculator. Turning points are where the graph obviously turns. As you can see on this, this looks like a cubic function. Next to the third, we have a turning point. We have a top, almost looks like a top of a parabola on the left here where it says local maximum. And then we have a turning point down here where it says local minimum. It's intuitively like it sounds, it's where the graph turns direction. It changes direction from going in upward to down or down to up. Okay? The y-coordinate of a turning point is the local maximum of a function if the point is higher than all the nearby points. And it's a local minimum if it's lower than all the nearby points. The reason why we call it a local max or local min and not just a max or min is that, as you can see, the graph continues on in either direction, and we can find points when we stretch further left or right that are larger and or smaller than the local max and min. So that's why they're just called local maxes and minimums. Turning points, what do they tell us about? Or how can we determine turning points? Some key facts to know. Turning points are polynomial functions. The graph of every polynomial function of degree n has at most n-1 turning points. So a first degree or a linear function, if you plug it in, 1 minus 1 is 0, has 0 turning points. And think of a line. Lines stay in the same direction. They do not turn ever. So that makes sense. If we have a quadratic squared, 2 minus 1 is 1 turning point. Well, it's a U shape, right? There's a top, there's a bottom. A cubic, a third power, 3 minus 1, 2, just like the joint here, and so on and so forth. Point 2, if a polynomial function has n distinct real zeros, then its graph has exactly n-1 turning points, and that's how zeros connect to the turning points. N distinct zeros, then it has exactly n-1 turning points. Now this is real zeros. Real zeros, so not all zeros, not imaginary zeros, but real zeros. They could be irrational or rational zeros, but not imaginary. Okay, so we're going to analyze the graphs of some polynomial functions here. Let's look at an example. So, analyze the graphs of polynomials. F of x equals x to the fourth plus 3x to the third minus x squared minus 4x minus 5. So what are we going to do? What do I want to find? Well, I want you to find the following. I want you to find the local mins, if they exist. Mins in plural, there might be more than one. The local maximums. Local maximums, or plural, or maximum or maximums. The x-intercepts. And then I want you to graph. So we're going to do all those things. We're doing what I'm going to ask you to do in class tomorrow. Problems from your book. So let's practice that right now. So to do that, we're going to use the graphing calculator. We're going to use technology. Okay, so go to y equals, let's type in, I already have x to the fourth in, so I'm not going to retype it, plus 3x to the third power. Let's go up here and change that to third power. And we're going to do minus, I have to type again, x squared minus 4x minus 5. So make sure you have the calculator. Make sure you're not missing any powers. Make sure you're not missing any subtraction signs. Okay. So I'm looking back at it. I'm going to check and make sure I don't have anything missing. Looks like I'm good to go. Okay, so we graph it. Okay, so I'm going to drag this graph out just for future reference. You can't do that with your calculator. I'll show you how to graph it by hand here in a minute. So we want to find the local mins and local maxes. Okay, so the local mins and the local maxes, they're the turning points. So local minimum or minimum. It looks like on this graph we have two. Now, if I look, the turning points, the maximum turning points from this, from our formula we have up here, the maximum turning points right here, n minus 1. So our power degree is 4. So max turning points is 4 minus 1 or 3. We have a maximum of 3 turning points. We have 3 turning points here. The 2 in green are your mins. The blue one is a max. There's our 3. So we want to find the local mins. How do we go about doing that on our graphing calculator? Okay, well, follow along with me. Hit second, hit trace. Let's find a minimum. If we see that down here, that's 3. Now you have to look at the graph first and identify where there is a minimum. So right here, we're already close to the right minimum, so I'm going to just find this one first. I hit enter on the left bound. I got my icon is blinking to the left of the minimum point. So I'm going to go down to the minimum and go past it because I need to write the boundary. You notice that the 2 arrows up at the top, these arrows up here, they are pointing at each other. Okay? They're pointing at each other, indicating look between these 2 arrows. Okay, so get rid of that. So now we do a guess. Just get somewhat close to where the minimum point is. And it tells us we get a minimum of 0.676 and negative 7.02. So I'm just going to approximate those as decimals. 0.68. Oops. Excuse me. Not 0.68. The first local minimum is negative 7.02. There's our local minimum at negative 7.02. Right? Remember the y-coordinate is our minimum. It occurs at the x-coordinate. The x-coordinate tells us where it's at, but the minimum local minimum value is negative 7.02. Let's find the other minimum value. We have to go back to 3. Okay, so now we already did that one. If I try to do a minimum and it's a maximum, it's going to give you an error. Okay, so if you start getting errors, you probably used the wrong one. You either used min, or it should have been a max, or it should have been a min. So I hit enter. I got left of it. It was blinking. Now I'm going to go, it's hard to see down there, but right at the boundary, right at the point, hit enter. Now once I guess, I get down as close as I can. And it says a minimum value at negative 2.28 and negative 9.61. So my minimum value is, other minimum value is negative 9.61. So those are 2 minimum values. And I'll label the coordinates here just so you can see where they correspond. Negative 2.6, or excuse me, negative 2.3. And negative 9.61. And then over here, that's this point, right? And then over here, we have negative, or positive 0.68 or 0.7. And negative 9.61. So those are our 2 local minimums. Now we have to find the local max. Find the local max, it's the same process. We go down here to number 4. This time it's in a minimum. Let's say it's similar, I should say, not the exact same. There's a different function. Left bound, I've got to get to it. So here, there's the point. I want to be left of it. The closer you get, the more accurate it is. That's why I try and get within a couple clicks away from the actual max or min. So there we go, right bound, and now we're going to guess somewhat close to where the max looks like it is. And I get negative 0.65, negative 3.47, negative 0.65, and negative 3.47. There it is. And so my local max, positive, 3.47. So one local max, two local mins. So we have found those values. Now we want to find our x-intercept. Our x-intercept, we're going to find that from the graph as well. Our x-intercept is where the graph crosses, and let me do it here, where the graph crosses the x-axis. The red dots indicate the x-intercepts. So let's find those. There's more than one way we can do it. You can find zeros, go to where it says 0, number 2. But I think the faster way that we've learned already is just intersect. If I hit enter on number 5, and I hit enter twice, because remember we put y equals 0 into y2. Let's try that again. Oop, I had it. Sorry about that. Let's try it again. I went too soon. The calculator was going slow here. Enter, enter, enter. 3 enters. 1.42, y equals 0. So our first 0 is 1.42. 0, that's our first point. So our first x-intercept is 1.420. Let's go back and find the other one. Second trace. We're going to do intersect again. Hit enter. And then because we put y2 in the second line, the cool thing about it, after you hit enter, you just arrow over close to that second intersection point. And we get negative 3.047 and 0. So negative 3.070. It's our second x-intercept. 3.070 on the graph. Okay, so we found all the points. Now, what if you're in a class, for me, and I asked you to graph this by hand in class tomorrow, because I can't see everybody's graphing calculator all at once to grade it. So I have to have you reproduce this. Okay, not copying it on the back of the book, not just on your paper going, it's a W. That's not graphing it. Okay, so you need a rough approximation of it. So this is how you go about doing that. You make your XY grid, and this will help you out if you're in pre-calc and they just ask you to graph by hand to plot these points. Okay, 1, 2, 3, 4, 5, 7, 8, 9, 2, 3, 4, 5, 6, 7, 8, 10, 2, 7, 8. So I just make a grid, and you can use whatever scale is easiest for you. I'm just going by 1, as you can see, in all directions. I'm labeling just a few points, not every point on the graph. What I'm going to do is I'm just going to plot these points that I found approximately. Okay, so I found the coordinates of my x-intercepts to be negative 3.07 and 0. Negative 3.07 and 0. And 1.42 and 0. I found my local max to be negative 0.65 and negative 3.7, negative 0.65, negative 3.47. And I found my local mins to be at 0.68, negative 9, negative 9.61, and negative 2.3 and 9, or negative 2. Excuse me. Negative 2.3, oops, and 9.61. Oops. I see a mistake in there over there. You probably caught it already. This one should be 7.7, I should say. We have to fix that over here. I put negative 9.61 twice. This one should be negative 7.02. That's a drawback of you guys not being here to point that out right away. But I did catch it eventually. So I have those 3 points. Now all I do is I would look at my graph. Yeah, I don't have it already. I would look at my graph and I would say, okay, it makes this kind of W shape. So I'm just going to roughly trace a W shape on my graph. down to my minimum. Just kind of connect the dots. And that is the graph approximated by hand. Okay? But of course you have the graphing calculator. If you it's multiple choice, you won't have to do that. But if you have to ever do it by hand, find those local mins, find the local maxes, find the x-intercepts. That should be enough points to graph it for any other class, I would think. Last problem, you're going to have these problems in class to work on as well, so I figured we pick one of them and show you how to do it right now. This is the ACT likes to word questions this way. Here's column A, column B, and then they'll have answers. The quantity in column A is greater, the quantity in column B is greater. The two quantities are equal, and the relationship cannot be determined. Okay, so they're going to give you some expression, plug in a number, in this case, negative x to the fifth when x equals 1, and x to the fifth when x equals negative 1. So you have to plug it in and evaluate each expression and then determine what the right answer would be. So for column A, negative 1 to the fifth, and column B would be negative 1 in parentheses to the fifth. Well, negative 1 to the fifth, if we plug that in our calculator, minus, oops, let's get out of that mode, negative parentheses 1 to the fifth is negative 1. And then if we change it, put the parentheses around negative 1, negative 1, that's not why my calculator wasn't responding there, we get negative 1. So, what happened here? Is A greater than, oops, I forgot to put the first negative 1 down. Is A greater than B? Nope. Is quantity in B greater? Nope. Are the two quantities equal? Yes, they are. So our correct answer for this is answer C. So that's how you're going to go about doing those in class tomorrow. I'll have a worksheet for those as well. So let's revisit. Did we hit our targets? Today we did use a graphing calculator to approximate the zeros of polynomial function and the turning points. Put that in. And the turning points. Okay, I think we did that. We're going to do more practice in class tomorrow. I know it's calculator section, so it's kind of hard to practice at home if you don't have a graphing calculator, but hopefully you took the notes, paid attention, maybe wrote down some steps along the way to help make it a little easier for you in class and to help your peers out as well. We'll see you in class tomorrow.